Once again, welcome you all to the lecture number 4 of week 1. As a quick recap, in the last lecture, that is lecture 3, we started our discussion by solving some of the questions of practice problem 1 and 2. From there, we moved on to the sign binary numbers, and the discussions focus on the sign magnitude number, the sign complement, that is the ones and twos complement, and by solving questions on addition and subtraction using the sign complement system. Today, we will begin our lecture session by discussing some of the questions of practice problem 3, and from there our discussion will move on to binary codes. The first question is the complement of a binary number is. So, let us assume a decimal number, that is minus 9. So, first represent the decimal number 9 in binary in sign magnitude form. So, we know that the most significant bit represents the sign bit and the remaining is the data bit, right. So, the most significant bit I am representing first plus 9. So, therefore, my most significant bit will be 0, then 1 0 0 1. I will take the ones complement of the binary number, will complement each of the binary bits starting from the least significant bit 1 to 0, then 0 to 1, then again 0 to 1, 1 to 0, 0 to 1. Now, we get minus 9. Again we take the complement of this number, you will see that you get the original number. That means, you start from the least significant bit 0, complement it 1, 1 complement it 0, 1 again complement it to 0, 0 complement it to 1 and 1 again complement it to 0. So, therefore, the answer is the complement of a binary number is the number itself. The next question is the minimum number of bits required to represent a negative decimal number, that is minus 11 in 2's complement arithmetic. In the last class, we learned that to represent the lowest negative number in 2's complement form, the number of bits required is minus 2 raised to n minus 1, where n is the number of bits. If I take n is equal to 4, minus 2 raised to 4 minus 1, that is minus 2 cube. So, the smallest negative number you can represent it is minus 8 only. Therefore, to represent minus 11, the number of bits required is 5, that is 2 raised to 5 minus 1, that is 2 raised to 4, that is equal to minus 16. The next question is find out whether 8 bit 2 sign complement arithmetic can be used to add the two decimal numbers are 140 and 40. Again in the last class, we learned that in 2's complement the highest positive number that can be represented using n bits is 2 raised to n minus 1 minus of 1. With 8 bits, the highest positive number that can be represented is 2 raised to 8 minus 1, that is 2 raised to 7, which is 128 minus 1, that is equal to 127. Therefore, addition of the two decimal numbers, that is 140 and 40, we require 9 bits, because if I take 9 bits, 2 raised to 9 minus 1, that is 2 raised to 8, which is 256 minus 1, that is 255, I can easily represent, because my addition of 140 plus 40, it comes out to be 180. Therefore, how many bits we require? We require 9 bits. Now, moving on to the next. Perform the arithmetic operation. We are given two decimal numbers, that is minus 36 minus of minus 13 using sign 2's complement representation. So, we know how to represent a negative number in 2's complement form. So, therefore, first we will represent, that is the decimal number minus 36. So, first we will write plus 36 in sign complement form, okay, fine, and then we take the 2's complement of the number. So, plus 36 we represent it as 0 0 1 0 0 1 00. You know that the most significant bit represents the sign bit, because I am representing the decimal number plus 36. So, therefore, the most significant bit will be 0. I will take the 2's complement. You know how to take the 2's complement. We will start with the least significant bit. So, we will start with the least significant bit is 0, then followed by 0, then we have got 1. So, first you see the number 1, and once you get the bit value as 1, then you complement the remaining bits up to the most significant bit. So, therefore, the next bit is 0, we complement it, it becomes 1, again 0, we complement it to 1, 1 we complement it to 0, 0 again complement 1, 0 again complement 1. The number which we get right now is decimal number minus 36, to which we have to add the decimal number 13. So, that is shown, we have added it up. Why? Because minus 36 minus of minus 13 can be represented as minus 13 plus of plus 13. So, therefore, we add the binary numbers minus 36 and the binary number plus 13. So, the result which we obtain is starting from the most significant bit 1 1 1 0 1 0 0 1. You can see that there is no carryover from the most significant bit. The sign bit is 1 and the answer is negative. Therefore, take the 2's complement to obtain the final answer, which you get it as starting from the most significant bit 0 0 0 1 0 1 1 1, which is, as I told you earlier, the sign bit is 1, therefore, the answer is negative and the answer is minus 13, the decimal number minus 13. Now, we are moving on to the next topic, that is binary codes. Binary codes can be classified as numeric codes and alphanumeric codes. Numeric codes represent numeric information. Alphanumeric codes are used to represent alphanumeric information, that is decimal numbers, the letters of the alphabets, symbols and control characters. So, we will first start with the numeric codes. The first numeric code which we learn is the binary coded decimal, popularly known as BCD code. In BCD code, the digits of a decimal number, that is the decimal digit 0 to 9, are encoded in a group of 4 binary bits. All BCD codes have at least 6 invalid code words. So, therefore, we know that we can represent the decimal number 0 to 9 in BCD, and after that you have got the invalid codes right from the decimal number 10 to the decimal number 15. Now, we will take an example, convert the decimal number 34.25 to BCD. So, what we know is that we have got 34, that is the integer part, and you start with the digit in the units place, that is 4. So, you have to represent the decimal number 4 in 4 binary bits. So, we know that decimal number 4 in 4 binary bits, it is 0 1 0 0. Then we have got the decimal number 3, again you have to represent in 4 binary bits, which comes out to be 0 0 1 1. So, the integer part is now converted into the BCD code form, and now we will go for the fractional part. After the decimal point, we have got the binary number 2, again you encode it using 4 binary bits, which comes out to be 0 0 1 0. Then we have got 5, which is 0 1 0 1. So, therefore, 34.25, the decimal, when we convert to BCD, we get the answer as 0 0 1 1 0 1 0 0, the decimal point or the binary point, I say 0 0 1 0 0 1 0 1. Then again the codes can be further classified as weighted and non-weighted codes. So, weighted codes, the weighted codes are those codes which obey the position weighing principle. That means, each position has got certain weight. The weighted codes may be positively weighted or negatively weighted codes. For each group of 4 binary bits, the sum of the weights of these positions where the binary digit is 1 is equal to the decimal digit which the group represents. The examples of positively weighted codes are the 8421, or we call it as the BCD code, the 2421 code, the 5421 code. The examples of negatively weighted codes are 642 minus 3 code or 84 minus 2 minus 1 code. Then we have got the non-weighted codes. Non-weighted codes are those codes which do not obey the position weighing principle. The common examples are XS3 code and gray code. Now, we come to this table. On the left hand side, that is column 1 represents the decimal digit starting from 0 to 9, and we see that column 2 the weighted codes are there, the positively weighted codes, the decimal number 0 in positively weighted codes. Which are the positively weighted codes? Column 2 is a positively weighted code, that is 8421 code. Then column 3 is 2421 code, and then column 4 is 5421 code, and then column 5 we have got the negative weighted codes, that is 84 minus 2 minus 1, and then we have got 642 minus 3, and the last column, that is the column number 7, we have got the XS3 code. So, now let us take an example. Suppose the decimal number 3 in 8421, starting with the most significant bit, the weight is 8, 0 into 8 raised to 0 is 0. Then the next bit is 0, again 0 into 4 raised to 0, again 0. Then we have got 1, 1 into 2 raised to 1, that is 2, plus 1 into the positional weight 1, that is 1. So, 2 plus 1 we get the decimal number 3. If we take the same decimal number 3 in 5421 code, you can see that again it is represented as 0011, because if I multiply the weight 0 into 5 it is 0, plus 0 into 4 again 0, plus 1 into 2 that is 2, plus 1 into 1 1, that is if we add all it 0 plus 0 plus 2 plus 1, it comes out to be 3. If we take one example of the non weighted codes, that is the 84 minus 2 minus 1 code. If we see that for the same decimal number 3, 0 into 8 raised to 0, it is 0, plus 1 into 4 raised, that is 4, plus 0 into minus 3 is again 0, plus 1 into minus 1, that is minus 1. If we add it 0 plus 4 plus 0 minus 1, which comes out to be the decimal number 3. Now, we come to the sequential codes. Codes in which each successive code word is one binary number greater than the preceding code word. The 8421 and XS3 code are sequential codes. The sequential codes can be used for arithmetic operation. Now, we come to the next type of code, that is the cyclic codes. Codes in which each successive code word differs from the preceding one in only one bit position. So, the example is the gray code. The gray code is a cyclic code and is commonly used for translating analog quantity to digital form. So, we use the gray code principle for measuring the speed of a motor shaft. Then comes the reflective code. A reflective code is one in which the least significant bits for the code words starting from 2 raised to n minus 1 to 2 raised to n minus of 1 are the mirror image of code word from 0 to 2 raised to n minus 1 minus 1. The gray code is a reflective code. So, we come to the next table. Here we have seen that a gray code is there. So, we can see that the decimal numbers are represented on the left hand side column, that is starting from the decimal number 0 to 7, and you can see that after 3 I put a dark line. So, if we take the least significant bits, you see that is if we take 4, that is 1 1 0. So, if we take the least significant bit, that is 0 1, you can see that it is exactly matching with the decimal number 3, and only the most significant bit is being complemented. Similarly, if we take 5, the two least significant bits and the corresponding bit, that is 1 1, you can see that it is matching with the decimal number 2, and only the most significant bit of 2, which is 0, and it is getting complemented in decimal number 5. Similarly, if we take 7, you can see that the two least significant bits, that is 0 0, it is just reflective in the decimal digit 0, and only we see that the most significant bit, that is in 0, it is 0, and it is getting complemented in the decimal number 7. So, as I told you earlier, the gray code applications are in transmission of digital signals, as it minimizes the occurrence of errors, and it is mainly used in instrumentation and A to D converters. We will come to the next, that is alphanumeric codes. Starting with the ASCII code. The ASCII code, which we call it as the American Standard Code for Information Interchange, it is a 7-bit code. The code was first established as a standard in 1967. Because it is of 7 bits, the code represents 128 alphanumeric characters. The characters are 95 printable characters, which includes the 26 uppercase and 26 lowercase letters of English alphabet, the decimal digits 0 to 9, and 33 special characters consisting of mathematical symbols, punctuation marks and space character. The code also represents 33 control characters of communication devices like teleprinters, punch cards and paper tapes, which are right now obsolete. Now, we come to the next alphanumeric code, that is known as the EBCDIC code. The EBCDIC, that is Extended Binary Coded Decimal Interchange code, is the widely used code. The code was created by IBM. It is an 8-bit code and thus can accommodate up to 256 characters. Now, we will come to the error detection and correction code. We know that data can be corrupted during transmission or during storage. The contents of the received data is altered or data error has taken place during transmission or during storage. In digital system, the data bits gets changed from 0 to 1 or 1 to 0. The error in data can cause serious problem depending on the type of application. Suppose if it is a security information which is to be passed on, suppose if it can be either an audio signal or a video signal. So, you know that if data gets corrupted, so what are the significant issues which we may create, and therefore, error detecting and correction codes are used to find out whether the data which has been transmitted got corrupted during the transmission or the storage process. The two types of error in binary data are single bit error or burst error. In single bit error, the error occurs only in one bit in the data word. As an example, you can see a data having 4 bits 1, 0, 1, 1. So, we can see that one of the bits during transmission or during storage, you can see that the bit after the most significant bit, that is 0, gets changed to 1, and now you can say this is the data which has been sent, and the data received you can see is that what is the data we received 1, 1, 1, 1. So, this type of errors where an error takes only in a single bit, we call it as a single bit error. Now, we will move on to the burst error. In burst error, the error occurs in 2 or more than 2 bits of the data word. So, again as an example, we can see a data word 1011, and we can see that in 2 bit positions, we can see that the data which has been sent is 1011 and that the data which we receive is 110. That means 0 as seen by arrow, it has changed to 1, and the least significant bit, that is 1, has changed to 0. So, therefore, at the receiving end we get a data word as 110. That means, we see that 2 bits values have been changed, and therefore, such type of errors are known as burst errors. Now, we come to the error detection code. Error detection codes are of the following types: single parity check, 2-dimensional parity check, checksum, cyclic redundancy check, or in short we call it as the CRC. In this lecture, we will only focusing on the single parity check. The simplest technique for detecting errors is by adding an extra bit to the data word to be transmitted and is known as the parity bit. There are 2 types of parity. One is the odd parity. In odd parity, the parity bit is set to 1 or 0 such that the total number of bits in the code word is an odd number. So, we have got the data word, that is the data bit consisting of 0, 0, 1, 1. So, now how many ones are there in the data word? So, there are only 2 ones, that is an even number. To make it an odd parity, in the parity bit we will add a bit value 1. So, therefore, the total number of ones are 3. Now, we come to the next example, that is the even parity. The even parity, the parity bit is set to 1 or 1 such that the total number of bits in the code word is an even number. Fine. So, we just see an example over here. We have got 0, 0, the data word, 1, 1. The number of ones in the data words are even. Therefore, our parity bit is 0. In the bottom of it, you can see that another data word represented as 0, 1, 1, 1. So, there are 3 ones. That to make it an even parity, in the parity bit we add bit value 1, and if you count the total number of ones, you can see that there are 4 ones. Therefore, the parity is even parity. So, therefore, if there is any change, suppose you take in the second example, during transmission, if one of the value changes from 1 to 0, what will happen? You can see that the number of ones becomes odd. So, therefore, it can be clearly detected that a error has taken place during transmission. Therefore, change in any odd number of ones, the error will be detected for an even parity. So, you can see an example in this table. You have given the data bits decimal number 0 to 9. To make it an even parity, you can see that for the decimal number 1, in the parity bit we have added a 1. Similarly, for decimal number 9, you can see that how many ones are there? 1, 0, 0, 1. There are 2 ones, that is even. Therefore, in the parity bit we have made 0. Fine. And the most important part is the distinction between a valid and invalid code word is based on the distance. What is a code word? A code word is the combination of the data bit plus the parity bit. So, how we make a distinction between a valid and invalid code? That is based on the distance. So, distance d between 2 code words, as you see in the figure, C I and C j denotes the number of bit positions in which the code word differs, or how many bits in C I and C j are different. So, C I you can see that it has got a code word 0 1 0 0 1, and in C j you have got a code word 1 1 1 0 1. So, how many bits have changed? You can see the most significant bit in C I is 0 and C j it is 1, and followed by that it is 1, and in C j also it is 1. Then in C I we have got 0, but in C j it is 1, and then the next bit, that is 0 in C I, again it is 0 in C j, and the least significant bit it is in C I it is 1 and C j also it is 1. So, there are only 2 changes in the bit position. Therefore, you can say that the distance between the code word is 2, and why? Because there are 2 bit positions where the bit values change from 0 to 1 or 1 to 0. The minimum distance d m to detect 1 bit error in a code word is 2. To generalize it, the minimum distance d m I represent as d with subscript m is equal to k plus 1, where k is the error bits. Now, we will come to the error correction code. A code is said to be error correcting code if the correct code word can be obtained from an erroneous code word. The key requirements of the error correction codes are detect and locate the erroneous digit and correct the erroneous digit. So, we will be learning one popular error correction code, which is a single bit error correction code, that is the Hamming code. Hamming code is an error correcting code. It is constructed by adding p parity bits to the group of d data bits to form a p plus d bit code word. So, what are the basic principles of a Hamming code? First, form the p plus d bit code word, then the number of parity bits one requires. So, the number of parity bits p must satisfy the inequality 2 raised to k greater than or equal to d, that is the number of data bits, plus k, that parity bits, plus 1. Suppose if the data bit is 4 and if I take k is equal to 2. So, 2 raised to 2 is 4, and here on the right hand side, that is the data bit is 4, k I have taken 2, 4 plus 2, that is 6 plus 1 7. So, the inequality fails. Therefore, if I take k is equal to 3, 2 raised to 3, it is 8, greater than or equal to d is 4, k is 3, 4 plus 3, that is 7, plus 1 8. That means, the left hand side and the right hand side of the equality are same. So, therefore, it satisfies the inequality. So, therefore, for a 4 bit data word, you require 3 parity bits. So, now the second question is where to position the bits. Each of the bit position of the code word assign the value 1, 2, 3, 4 starting from the leftmost bit up to the rightmost bit. So, I have given an example where you got 4 data bits represented as D1, D2, D3 and D4, and the positional values right from the leftmost bit I mark the position value as 1 going up to the rightmost bit, which the position value I have made it as 7. Now, where to place the parity bits? The parity bits P1 to P3, because we in our example we have got 3 parity bits P1 to P3 are assigned position numbers that are powers of 2, that is 2 raised to 0, that is position 1, then 2 raised to 1, that is position 2, 2 raised to 3, that is position value 8, 2 raised to 2, that is position value 4, and then 2 raised to 5, that is position value 32, and so on. Now, we will do an example. Design a Hamming code for decimal number 7 expressed in BCD as 0, 1, 1, 1. The data word has 4 bits. The number of parity bits P required to fulfill the equality criteria is 3, where 2 raised to 3, that is 8 is equal to 4 plus 3 plus 1. Assign the position of the parity bits and data bits as per the rule. So, we can see that where 2 raised to 0 place P1, 2 raised to 1, that is position 2 I place P2, and 2 raised to 2, that is position 4 I place P3. The remaining positions, that is position 3, 5, 6, 7 are filled by the data bits, that is 0, 1, 1, 1. Now, obtain the bit value of the parity bit. You first prepare the parity table as shown in table 2. Then perform the exclusive OR operation of the bit position from the table whose bit values are 1. Now, we have got the parity table. You can see that the left hand side column P3, P2, P1. So, there are 3 parity bits, leaving 0 I started with 1 to 7. So, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. The top row shows the position value, that is 1, 2, 3, 4, 5, 6, 7. Now, what you have to do? Exclusive over the bit position of each parity rows whose bit values equal binary value 1. So, we will start with P1. You can see that in position 1 you have got the bit value 1, similarly in position 3, position 5 and position 7. Therefore, I exclusive over it, 1 exclusive over 3, exclusive over 5, exclusive over 7. Similarly, P2, that is 2 exclusive over 3, exclusive over 6, exclusive over 7, and similarly the parity bit P3, that is 4 exclusive over 5, exclusive over 6, exclusive over 7. Compare the exclusive over position with the bit value of corresponding bit position of table 1. So, if I compare it, you know that the P1 is equal to 0 exclusive over 1. So, how I got it? Because if you see P1, that is 1, 1 itself is what in your table 1, that is the parity bit 1. Therefore, I have removed it. The remaining one is 3, 5 and 7. So, what all is placed in 3, 5 and 7? 3, 5 and 7 if we come to table 1, that is 0, 1, 1. So, there how many ones are there? There are only even number of ones, therefore, if you exclusive over it, it is 0. Similarly, P2 if we see that it is 2 exclusive over 3 exclusive over 6 exclusive over 7, where the position 2 represents the parity bit P2. Therefore, the remaining are 3, 6 and 7. Put the corresponding values, again 0 exclusive or 1 exclusive over 1, there are even number of 1, therefore, the value is 0. Then we have got the parity bit P3, P3 is 4, position 4 itself is parity bit P3, therefore, with 5, 6 and 7. So, what is the data value, what is the position value of the data bit in 5? It is 1, 6, 1, 7, 1, there are odd number of ones, therefore, exclusive OR operation gives 1. Therefore, P1 is 0, P2 is 0 and P3 is 1. Now, put the validity of parity bits P1, P2 and P3 in the respective bit position in table 1 to get the Hamming code. So, P1 we have got 0, P2 we have got 0, then we have got the data bit, that is in position 3 0, then in position 4 we have got the parity bit P3 whose value we obtained 1, then 5, 6, 7 position values are the data bits 1, 1, 1. The Hamming code word for the data word 0, 1, 1, 1 is 0, 0, 0, 1, 1, 1, 1. For error correction, the check bits are C1, C2 and C3, that is equal to 1 exclusive over 3 exclusive over 5 exclusive over 7, which is equal to P1 exclusive over D1 exclusive over D2 exclusive over D4. Similarly, C2 that is 2 exclusive over 3 exclusive over 6 exclusive over 7, that is P2 exclusive over D1 exclusive over D3 exclusive over D4. Similarly, the check bit C3 that is equal to 4 exclusive over 5 exclusive over 6 exclusive over 7. This exclusive over we have got it by following the rules in the previous tables. So, 4 that is the parity bit P3 exclusive over the position 5 occupied by the data bit D2, then 6 that D3 and 7 D4. The error bit position is given by the binary word C is equal to C3, C2, C1 represented in binary. Now, we move on to some of the review questions. The distance between the code word 10010 and 11001 is, what is the answer? The answer is, you can see that there are changes in 3 places in the values and therefore, the answer is D, that is 3. In 7-bit Hamming code for BCD, the parity bits are at which locations? So, you know that the BCD number we require 4 data bits. So, how many parity bits we require? We require 3 parity bits, and where the parity bits are placed at which locations? At bit location 1, 2 and 4, that is 2 raised to 0, 2 raised to 1 and 2 raised to 2. That is the correct answer is B. Now, move on to the next question. Gray code is a non-weighted and cyclic code. The number of parity bits in a 12-bit Hamming code is, as we know that the parity bits position is, we place the parity bits 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 4. We have got one parity bit placed at position 2 raised to 0, that is 1, the second 2 raised to 1, that is 2, the third is 2 raised to 2, that is 4, position 4, and the fourth is 2 raised to 3, that is position 8. So, how many parity bits are there? That is the correct answer is option A, that is 4. There is a practice problem, please practice it, and in the next lecture we will start learning about the logic gates and the Boolean algebra. The next week we will start with week 2, lecture 1. Until then, happy learning. Thank you.